Hi. So thank you for being here. Today I'm going to talk about lower bounds on the overhead of quantum correction low dimensions. This is a work that was done with Omar Fawzi, who's right there, and Shayeghi, who both work at ENS. Right, so the general issue that quantum correction tries to solve is that if you have like a quantum circuit, I can't see the laser. Okay, if you have a quantum circuit, you might input a state rho into it, and over time, errors are going to accumulate, and eventually you'll end up with a state that is different from the one you started with. One way to solve your issue is that while your state is in the computer, you might be able to apply some kinds of operations which eventually will allow you to correct some of the errors, and you'll end up with a state rho that is kind of close to the state you started with. The problem is that generally, the class of operation you can do is kind of restricted. Our computers are not all powerful, so like, it is quite natural to ask the question, if they're restricted, is there a trade-off? Like, is there a limit to the extent of which we can correct for errors? In particular, one setting that has gathered quite some interest over like the last 20 years is what happens with low dimensions. If you have like a quantum computer that is based on transmon qubits or spin qubits, oftentimes the kind of operations you can do are like limited by locality. So you might have, for example, some like local quantum operations depicted in green. You might have like some kind of arbitrary classical computation on a classical register X, because you have access to like rather good classical computers. And also you might be able to do some controlled operations between your classical register X and your noisy quantum register Q. And we would like to be able to formalize this setup, which might not be terribly obvious. So the quantum register is just going to be a set of qubits. The classical register, although it is technically supposed to be a set of bits, we are actually going to treat it as just like a normal Hilbert space. The circuit is going to be a sequence of CP/TP maps, and those maps are going to have to obey a certain structure, because we don't want to be able to take the qubits from our noisy quantum register, put them in our classical register, and then export them at the end of when we want to retrieve our information. So to ensure that we can't do that, the kinds of maps that we allow for have to be separable between the quantum register and the classical register. Further, the operations we do on the quantum register, since we want them to be local, we're going to assume that further that the Krauss element of those maps can further be broken down into smaller operators. Each of those operators there have to act locally in a ball of bounded diameter. So like, this is what one operation would look like. You have like a bunch of Krauss elements acting locally on your qubits, and you have like an arbitrary, potentially, operation on your classical register. In the end, this is what our setting looks like. We have, we input a state. We have like our quantum memory, classical memory initialized in 0. We're going to undergo some layer of depolarizing noise, and then we can do like a local operation of constant depth, and then another layer of noise, and then on and on and on and on. And at the output of the circuit, so like there at the end, we would like to retrieve a state rho prime that is close to the initial state rho. Our main result for the 2D case can be stated in terms of a few parameters. So you have n, the size of your quantum register, k is the number of logical qubits you can encode, and f is a quantity that quantifies how well your error is suppressed. So although the expression might be a bit unreadable there, the idea is if you can correct up to error epsilon, then epsilon can be expressed as p to the f. So like f quantifies how, like to what extent is your error exponentially suppressed. And ideally, what we would like is f to scale polynomially in the size of the system so that we can have like some kind of exponential expression. So in 2D, this is what this gives. So like the overhead, so the number of physical qubits you need per number of logical qubits scales as square root of f. If you're familiar with quantum codes in general, you can think of f as being the distance. And so what this states essentially is that if you want your error suppression to increase as you scale up your system, the overhead is necessarily going to grow. So as I mentioned before, this question had garnered some interest before. The most noteworthy result is the BPC paper from 2009, where they show that if you have a local stabilizer code, so like you have a stabilizer code and all the generators are local in 2D, the region in blue there is like the space of codes that you might be able to find, the space of codes that exist. So like this is K, this is D. You can observe a trade-off between K and D, right? But they did not consider the possibility of doing classical computation, because indeed you might do some operations that are further, like far apart, and then combine the result classically in your all-powerful quantum computer, and then obtain a correction that would be better without this classical communication. And in 2021, Delphos, Beverley, and Beverland and Tremblay showed that indeed, if you have access to classical communication, you can reach this point there. And this naturally leads to the question, okay, well, if you include classical communications, or classical computation even, what does that give? And so our result essentially for 2D shows that what you're limited to is like this yellow region. An application of this result is the following. So if you're unfamiliar with quantum codes, we do speak of them often in terms of n, k, and d. N is the number of physical qubits, k is the number of logical qubits, and d is, once again, a parameter that quantifies how well you can suppress errors. If you have an LDPC code and you want a constant depth syndrome measuring circuit, we know that under a certain noise level, measuring the syndrome is enough to be able to correct errors. Like you measure syndrome, you apply your Pauli correction, all of this just requires some classical computation which we can do in our setup. And what this says that if such a constant depth circuit exists, you still have to obey the same trade-off. We can like take those parameters, plug them in the bound before, and this is the trade-off we obtain. Good. So now I'm going to move to how the proof works. The general idea is if you have a code whose, I'm going to focus on K and D from now, because they're just easier to talk about rather than talking about F. So if K and D are large, the code states in your code are going to be entangled. And tracing out, like when you have noise, this noise is going to destroy this entanglement. And if you have a circuit T that is able to correct the state, like go back to the original state, this circuit is going to be slow at building up entanglement, right? So like this, you have this contradiction of the state I want to produce is entangled, but the circuit is local, and so it takes some time to build up entanglement. So I get this kind of trade-off there. Pictorially, this is what we're going to do. We have like our lattice. We divide it into squares. Each square is going to have size at most d. We're going to have a few of the squares, so like we're going to have at most n over d of the squares. And each of the squares is going to have at most square root of d neighboring qubits. Right. Okay, so I think sorry, it seems like there's a slide missing. Right, so to quantify entanglement, we're going to use the relative entropy of entanglement. Right, and we're going to show that among all of the squares, there's one in particular that is highly entangled with the rest. And the way that we're going to quantify this is that the entanglement between that specific square, the rest of the lattice, and the classical register is lower bounded by this quantity. So you can see that if K and D are large, this quantity goes up. On the other hand, we're going to show that rho primes, like the state we obtain at the end of the circuit, has bounded entanglement. So we're going to see that the entanglement between the square and the rest of the system is at most delta, well, delta is the depth of the circuit, times square root of D. And eventually we can combine all of this, and this gives a lower bound on the depth. Right, so how do we show that those states are entangled? It's quite easy. If you consider a code space, and you have a basis for that code space, the uniform mixture of those code states are going to give you a state of high entropy. Specifically, the entropy of the state is going to be K. And due to the subadditivity of the entropy, we know that if you have a state on that lattice that has high entropy, there's at least one of the squares that has high entropy. And this is what this gives us there. Now, a property of quantum codes in general is that since A is small enough, namely it contains less than d qubits, this property is actually valid for any code states. You can show that if a property holds for less than d qubits, then it holds for any code states in the code. Another property of quantum code is that the entropy on a region containing less than d qubits is equal to the coherence information, which was supposed to be defined in a slide that has since disappeared. And this is a way to quantify entanglement, actually. So like we show that between A and its complement, so the rest of the lattice, the coherent information is larger than this quantity. And eventually, we use yet another quantity to quantify entanglement, the relative entropy of entanglement, to show that this is lower bounded by this is lower bounded by that. Trust me on this. And we do obtain a lower bound on the entanglement between A, the rest of the system, which is equal to this. Great. And so now we do have to show that we have showed that the system is entangled. We need to show that the circuit takes time to build up that entanglement. And now the definition of the relative entropy of entanglement is going to be crucial. So the way that the relative entropy of entanglement is defined between a system A and another system is the minimum of all states tau, such that tau is separable between A and that system, of the relative entropy. And the relative entropy has a nice property, namely it is monotone under CPTP operations. And so we might be tempted to note that, well, if we apply one step in the circuit to both states, then the relative entropy of entanglement indeed does decrease. It is more than what you had before. And so you should end up with a relative entropy of entanglement that decreases. The problem is that the state you end up here, so like tau, or like tau after you apply a step in the circuit, is no longer separable. So like here you do need the state to be separable, and here you don't have that. So that's an issue. And the way we can correct for that is that since the circuit is local, there's only the only place where entanglement might happen between A and the rest of the system is actually at the boundary of A, right? So if we apply that circuit to tau, tau might no longer be separable, but it almost is in some sense. You just have to like remove this region there. And this is exactly what we do. And it does give us that the relative entropy of entanglement after one step of the circuit is simply lower bounded by what we had before, plus a correction that is proportional to the boundary, because this is the only place where entanglement might have happened. And eventually, what we obtain is that at the end of the circuit, since the circuit has depth delta, we obtain that the entanglement is lower bounded by this quantity, which is lower bounded by this quantity. Great. So we did obtain every step we needed. The entanglement is large. The circuit takes time to build it up. And so we have a lower bound on the depth of the circuit. Right. So some open questions that are left are that this kind of observation underlines that if you have a system with an area law, this system is quite bad at preserving information. And so it might be interesting to look into noisy circuits in general. Do they obey a kind of area law? That would be kind of interesting. The second thing we can note is that the definition of error suppression we consider here is quite restrictive. We require that the state at the end of the circuit is close to the state we started with, which, if you're only interested in, for example, measuring parallel operators, isn't that important. Like, if you only want to make a measurement on your final state, it might be that the output of that measurement can still be protected. And finally, there has been some work interested in what happens if you have a local random circuit. Can you generate a good code out of that? And this kind of work does tell you that your random circuit has to have a certain depth to reach a good code. That's it.
Thank you. We have plenty of time. Cool. Thanks for the night's talk. I was wondering if, it appears that in your proof, the locality of the circuit is really essential. Do you have any idea if you add a little bit of non-local operation, what happens? Do you have an idea if you need to add a constant number, a logarithmic number, or something like this?
Yeah, that's a great question. So actually, there is some work by Anirudh Krishna and myself on stabilizer code, and we show that in that context, if you want to break free of those limitations, you need to add a significant amount of non-locality, actually. And I would expect, in that setting, we haven't proved it explicitly, but I would expect something quite similar to hold.
Next. Oh, okay.
Okay, you were talking about 2D, fat. You were looking at the 2D case. Now, you were looking at a grid in particular. What if it were, some irregular arrangement of the lattice spacings, like a hyperbolic space? Would your results still hold in that case?
So, so the crucial thing is indeed that you can take the 2D space and separate it in a way that each region is not going to have a big boundary. And actually, it's even worse in the hyperbolic space. You can do that same procedure, where you take the hyperbolic plane, for example, and you separate it into regions of small boundary. And the bound here would be even more restrictive, actually.
Great.
Yeah.
Thank you.
Feel free to raise your hand while the other there's discussion, so I can just run to you earlier. Is that hand sort of raised? Okay.
Hello, thank you. So the code in the previous talk seems to be substantially below these bounds. Does that suggest anything about sort of the ability to decode it in low dimension, or any other implications of that sort of?
Right. So if I understand well, in general, concatenated codes are quite non-local, and yes, this would suggest that embedding it into D would be quite impractical without a trade-off somehow.
Thank you.
Yeah.
Anybody else? Still got some time. Just want to get the gist of this result. Locality constrains entanglement growth,
and entanglement is needed for error correction or protection.
Yep.
Is that fair?
Absolutely. Yeah.
Okay.
Good.
And the codes that you need?
So,
You do kind of a code independent approach with this info theory stuff, right?
sorry, I didn't catch that.
What kind of codes is this
Right.
covering?
This applies to any code.
Right.
Like it might be stabilized.
Well, any
or-
tensor product space code, right? Because you have little n.
Yeah, that's true. Yeah, so like a code in qubits. Yeah.
And qubits?
Yes.
Do you assume local dimension too?
Kind of explicitly, but like the proof would still adapt rather straightforwardly.
Okay.
Yeah.
Yeah, here we go. Okay, that wasn't even time. I planted my feet.
That was officially my fault. So you derived this upper bound on, in some sense, the efficiency of 2D local codes.
Yeah.
And you have at least sort of 2 points, with a 1 all the way on the right, which is, I guess, the surface code, and 1 in the middle on this triangle.
Yeah.
But do you think there is stuff all the way across that line, or is there some other constraint
all the
that
way
has yet
across?
to show its face?
Right. So actually, so in the surface code is there, right? And you can see that, okay, so you have the surface code. You can take like small patches of the surface code, right? And if you take a lot of those patches with patches that aren't too large, you can actually glide up and down
Okay, yeah.
this line. Yeah.
But can you do the same with the yellow line? Or is that harder?
Good question. I don't know.
Anybody else?
Thank you for your talk. I was wondering, early on you mentioned this third parameter f. I was wondering how that parameter how your proof adapts to integrate that parameter.
Right. Good. So this F here, so like here we use depolarizing noise channels, right? And this, okay. The reason why we use F and not D is that you might have a code whose distance is actually quite small, but it might still actually be able to correct noise up to a high probability. And so that's why the distance is like not the end all be all, if you will. F captures much better this ability to suppress errors. Yeah.
Maybe one more question, if there's any. Going once, twice, and let's have a hand for another great result.